So this is going to be the big equation. It's going to be our force equals our stiffness matrix K global times our nodal displacements. And we know that this is going to be 0, right? 0, 0, 0, 0, 0. So we only have, remember, U3X and U3Y because everything else was a fixed support. So just like the one-dimensional, that means we can cross out everything and all of the corresponding components, right? Cross those out, cross it out, cross it out, cross it out, cross it out, and so forth. So basically we're only left now with a 2x2 matrix, right? So after crossing everything out, we can look at everything only at the third node, right? So F3x, F3y is going to equal our global stiffness matrix at U3x and U3y, and that is going to be times U3x, U3y. Now, so now this is the actual matrix. This is the displacement matrix. This is just the slots that I'm illustrating. Now, how do we fill this matrix up? So we need to find the global stiffness matrix just at node 3, okay? In order to do that, big K equals AE. Now U3X, U3. Okay, so now remember, like in the 1D problem, we were adding every component that has a 3x and a 3y. So you literally do the exact same thing. You look at your local stiffness matrix and you match up everything that has a U3x and you add them into this component here. So let's look at our local stiffness matrices. So we've already done this. We've looked at our U3x column and we found our U3x row. That equals 0.6 squared. Okay, so go back down here. 0.6 squared is 0.36. So let's go 0.36 plus. We look around. Okay, we got a 3x here, 3x here. Oh, but it's 0. Okay, so we'll leave that one alone. And now over here we had another 3x column and another 3x row. Okay, so it's 0.36 again. So plus 0.36, and that's our first component of our 4x4, or sorry, our 2x2 matrix. Now we need to do the same thing with our y's. Look at U3y and U3x, so match those up. Okay, so we got U3y, U3x here and here, and this just gives us a 0, so we're going to leave that one alone. Okay, so 3x. Okay, so we got our U3y here and our U3x, so negative 0.48. So we'll go down here, negative 0.48. And now we can find anything else. So we have negative 0.48 for U3x, or U3y, U3x. Okay, so now we're looking at this matrix, and we've got our 3y column, and again our 3x column. So we're going to get 0.8 times 0.6, which is positive 0.48, plus 0.48. So now 3x and 3y. 3x, 3y, another 0 in this one. Looking at stiffness matrix number 2, we have our 3x again and our 3y, and it should be this one here, which is negative 0.48. So we'll shove that in, negative 0.48. And now our first stiffness matrix, 3x, 3y, it's going to be positive 0.48 because it's reflection of 0.8 times 0.6 because it's a symmetric matrix. So plus 0.48. Now the last one is this component. So we need to find everything that has a 3y and a 3y. So looking at our stiffness matrix 3, U3y, we have a 1. Okay, so add 1. 1 plus, looking at stiffness matrix 2, 3y, 0.64, and stiffness matrix 1, local stiffness matrix 1, 3y, we have 0.8 squared. So 0.8 squared is 0.64. Okay, so now we had an L. Remember, if on the local stiffness matrix 1, 2, and 3, we had a different L, right? It was 50, 50, and then 20. So we can't forget that L. It's going to be different L's for each stiffness matrix, right? So every time we had a component taken from stiffness matrix number 3, we had to divide it by 20. And 1 was the only component that we took from stiffness matrix 3, so that was the only component that we divided by 20. And the rest get divided by 50, because everything from stiffness matrix 1 and 2 are both 50 meters, so over 50 for every other component. And we know that this is 0, right? That equals 0. So evaluating these, this gives us our stiffness matrix, our global stiffness matrix, K, at our third node. So if you do this addition, this is what we get. Okay, so this is the global stiffness at node 3. So basically, I didn't cancel out the entire matrix. I've just chosen to only evaluate the properties at the node 3, because we remember from the matrix multiplication properties, if we have a 0 column or 0 row, any multiplication in that row is going to be 0. So this allows us, this property, just like what we did before with the 1D matrix or the 1D system, allows us to cancel or cross out those rows and not have to do any evaluating. So now we've got the global stiffness matrix for node 3. So now what do we want to do? We want to evaluate the displacements at node 3 now, right? That was the main objective of this problem. That's what we want to do. So same thing as one-dimensional. Recall that the force equals K times U. So we have our F3x, F3y. Now remember to be careful when you're labeling your forces here, because we're looking at stiffness matrix, global stiffness matrix for 3, right? So make sure you have your 3x and your 3y. So putting in our global stiffness matrix at node 3, this is what we get. And remember, AE is constant, so I'm leaving those out for now. And now we're multiplying by U3x and U3y. And looking back at our original problem, in the picture we've shown that we have a 50 kilonewton applied force in the x direction and a negative 100 kilonewton applied force in the y direction. So let's plug this into our equation, 50, 100. And now you can see how easy this is, right? It's literally the exact same thing as the one-dimensional problem now. We've simplified it, made it super easy, and now we just need to do matrix multiplication and solve for our displacement equation. So matrix multiplication, we can show that 50,000 newtons. Remember, area was 50 times 10 to the minus 4 meters squared. Modulus of elasticity, 200 times 10 to the 9 newtons per meter squared. And now, if we do the matrix multiplication, we have 0.0144 times U3x plus 0. Right, so that is basically it. This gives us our U3 equal to 0.0035 meters. Similarly with second force, so this was U3x. And now this gives us U3y equal to minus 0.00132 meters. So we've now solved for the nodal displacements at node number 3 using our global stiffness matrix for a two-dimensional problem. And I'll make a separate video where I solve for the internal forces for the same system using the same approach with all the same values. But for now, this was all we needed to do. We needed to solve for the nodal displacements at node number 3. Our U3 done, and our U3x and our U3y was done. So let's just recap. So basically the first thing you want to do is write this out every time. You're probably going to be given this, but you have your local stiffness matrix, your general form with all of your cosines. And what you want to do first, you want to find your stiffness matrices, your local stiffness matrices for every member. Every member is going to have a different local stiffness matrix. So you look at your first node, where you're going to consider first. I considered node 1, and it might be different. It depends on the way that you label things, but for member 1, that entails our node 1 to node 3, okay? So when you're labeling your stiffness matrix, your local stiffness matrix, make sure that you only have 1x, 1y, 3x, and 3y, because you're standing at node number 1, looking at node number 3. So that is important to keep straight. You can only have the nodes that are connecting your member within your local stiffness matrix. All right, so we had our angle of 53 degrees. We calculated our cos of that angle, our sine of that angle, plugged it into our big formula, our big matrix with all of our cosine and sine angles, and we got our local stiffness matrix for our first member. Did the exact same thing with the second member. We are standing at node number 2, looking at node number 3, so we have our 2's and 3's in our local stiffness matrix, and we had an angle of 127 degrees. Remember, we're always measuring from the x-axis, right? Always measuring from the x-axis counterclockwise of the node that we're standing at. Similarly, we did the exact same thing with member number 3, standing at node number 3, looking at node number 4. Our angle was 90 degrees, and we got this local stiffness matrix. Simple. And then we did our boundary conditions, right? So we found that the only nodal displacements were going to be at node number 3, because everything else had a hinge, or it was a pin support or a fixed support, so there can't be any movement. And then if we were to assemble the global stiffness matrix, we had to do a lot of running around, which I didn't really want to do because you don't really need to solve this problem. But remember that we have to find out each component, the matching components for every column and every row with our local stiffness matrix, and add them up. If we have anything overlapping, add them up, throw them in your global stiffness matrix. So then we're looking at the global stiffness matrix, F equals K global times U global. We had no movement anywhere except for at node number 3. So we were able to just, for now, temporarily eliminate all of those rows and columns out, which left us with a 2x2 matrix globally for node number 3. Now to populate that matrix, what we did, we found all of the matching x and y components for our local stiffness matrix, and whenever there was anything overlapping, we added them up, and this gave us the global stiffness matrix at node number 3, right? And then throwing it back into our equation, F equals K times U, our stiffness matrix, we then used multiplication and solve for the only unknowns, which were our displacements at node number 3. So we got our 3x of 0.0035 meters and 3y of negative 0.00132 meters. So in my next video, I'm going to look at solving for the reaction forces, or sorry, not the reaction forces, the internal member forces in each 3 of our members. So make sure you check that out. If you like my channel, if you like my content, subscribe, like, and share, and visit my website that I'll link at the bottom here. Thanks for watching.